I'm going to talk to you today about the Amazon and global change, partly because it's one of the big uncertainties going into the future. So as you know, we're living in a time of unprecedented change. Since I was born, the amount of carbon dioxide in the atmosphere, this red line here, has increased 100 parts per million. So over one human lifetime, that's the same amount of change as occurred over thousands of years when the glaciers melted and warmed to create the interglacials. So one of the things I want to put across is that the rates that we're seeing, as well as having CO2 levels outside the range of what has been seen in the last 600,000 years at least, we also are experiencing rates of change that are very much higher than anything experienced in the past. And that counts also for the temperature changes that we see now. Of course, the increased CO2 increases temperatures because it's a greenhouse gas, and we're now outside the envelope of past variability again for at least the last 600,000 years. And what we're headed for by 2100, the largest uncertainties are what we will do, how much more CO2 we will emit into the atmosphere. But the reason I'm talking about the Amazon today is because that organisms now, including humans, we're experiencing conditions that are far outside those that we and our societies and vegetation globally have experienced and evolved with before. So when I talk about I'm going to spend time talking about carbon as the thing I focus on in the Amazon. And that's because we're putting carbon dioxide into the atmosphere. Those are the red arrows. The natural carbon cycle is, of course, taking up and releasing much larger amounts of carbon every year as it transforms carbon dioxide in inorganic form on land through photosynthesis into organic carbon compounds that get returned again mostly to the atmosphere as carbon dioxide again through respiration and decomposition. And in the oceans, we also have large exchanges, largely physical-chemical ones, where you have the reaction of carbon dioxide with water and the dissociation to form bicarbonate and carbonate. This is one of the reasons we worry about elevated CO2 in the atmosphere, is that it's acidifying the oceans in ways that are measurable now. So we're putting tiny, relatively tiny, or now it's 10%, it's not quite so tiny, but the amounts we're adding to the atmosphere are operating the background of these large natural exchanges. And so the good thing for us is that things could be even worse, because about half of the carbon that we put into the atmosphere stays there, and the rest goes into land and ocean, so dissolving in the oceans and taken up by land plants. I'm going to be talking mostly about the terrestrial part of this carbon sink, which has been increasing over time. And another thing to point out is that it's highly uncertain. It's mostly the difference between things we can measure well, like what accumulates into the atmosphere over time, because we can measure CO2 in the atmosphere and it's relatively well mixed. And the amount that dissolves in the ocean, because we're measuring changes in ocean chemistry and using models of ocean circulation, we have relatively good understanding, we think, of the to constrain how much carbon dioxide is dissolving in the oceans. So of the about 11 gigatons or billion metric tons of carbon that we're adding to the atmosphere per year as carbon dioxide through fossil fuel emissions and deforestation, roughly a little bit less than half is accumulating in the atmosphere, and the rest is split between the ocean and land sinks, with the terrestrial sink partly, offsetting the deforestation sources. Some of that is through regrowth of the forests that were deforested. The other thing we can do is estimate where global carbon sinks are located. That's done by having a network, global network of observation stations where carbon dioxide levels are measured extremely precisely. And then if we know the wind fields that's mixing the carbon dioxide throughout the atmosphere, we can use those small differences from one place to another to infer what the carbon source or sink in between our sampling points were. And so when you do this at the global level, you can see ocean sinks are mostly in the cold, high latitude waters where deep waters form. But on land, the largest sinks are in tropical forests. And these are highly uncertain, partly because our understanding of the mixing of the atmosphere is at its worst in the tropics. And also because it's balancing large deforestation sources with sinks. But this is our best understanding to date, and I'll go through some of the answers there a little bit later on. The other reasons to study the Amazon, it's less than 4% of the land surface, but it's really a special place. It has about 10 to 20% of the world's biomass, which is about 200 billion tons of carbon stored, or 20 years worth of our present emissions stored in plants and soils. And these are vulnerable potentially to future global warming. It's responsible for about 16% of global photosynthesis, and it's one of the engines of the global climate and atmospheric circulation system, because there's so much energy deposited at the equator. Most of that is used to evaporate on order of 200 trillion liters of water a day. The recondensation of that in the atmosphere releases heat that also drives a lot of global as well as regional climate. The forests there, despite they're highly productive, despite having very poor soils, and one of the reasons is they have an intricate network to recycle nutrients like nitrogen and phosphorus, and that leads to very high biodiversity, and not just vegetation and animal diversity, but also people inhabiting this region are highly diverse with a lot of different languages. The plants and animals also emit a diverse library of chemical compounds that influence global atmospheric chemistry in important ways, and also influence cloud formation. But it's also a gap in our global observation networks. We really lack, until a few decades ago, good observations in this very large region. There's also some urgency to understanding what's going to happen as climate warms the tropical regions. And I think the best illustration of that is this plot below that just shows for every pixel globally in a model like the ones on the right, we have what the mean annual temperature and the mean annual precipitation of land is. And you can see the distribution in blue points is what is sort of the current distribution, and what we're heading for in 2100 with the high emission scenarios are the red points. And you can see that at high latitudes, if we warm things, there's a equivalent sort of climate and vegetation space that could move into the space that's warming. But when we get to the low latitudes, there is no tropical forest right now that exists at temperatures higher than 28 or 29 or 30 degrees Celsius. But that's where these regions are headed. So what will happen to those regions, we don't know. It could be that they just adapt to their optimal photosynthesis rates to higher temperatures, and they do just fine. Or it could be that we're warming so fast that the adaptation processes can't keep up. And then we'll have non-analog vegetation to what we have presently there. So that's really our main question: what's going to happen to these forests and the climate and ecological services that we depend on? And already things are changing rapidly. The same climate extremes that are hitting many of us globally are also hitting in the Amazon. This is pictures of net sort of precipitation anomalies, so very dry conditions in especially droughts, and very wet extremes. This year is very wet in the central Amazon. And so, these are also accelerating the rates of change. It's not just smooth change that we experience in climate. So the other complexity, if you're trying to understand what's the net carbon balance of this whole region, it encapsulates a lot of problems. One is that the deforestation sources are located mostly in this what's called the arc of deforestation. So the pink color here is outlining the more deforested regions where up to 20–25% of the forest has been cut, and only a lot of the places that remain are the outlines of the indigenous reserves or set aside lands. And these are regions which have a longer dry season. When you go to the west and northwest, there's less deforestation, and this is where a lot of the inferred uptake of the region is. But everything is changing with time, and that's one of the challenges of working these days trying to study the Earth system, is that it's in a state of rapid change, even as we're trying to study it and understand it. This is just a slide from a recent paper from Luciana Gacci and her colleagues. They're trying to do this atmospheric version of what's the net uptake or release of carbon in various parts of the Amazon basin. So they fly airplanes from different locations, make vertical profiles every 2 weeks. And then if you just look at the bars to the right here, then they look at how the winds are blowing from to get the air to the place where their plane flies. They look at the change in CO2 from upstream to downstream, and they infer the net release or uptake of carbon. In this case, the recent paper, there's only net release. So the Amazon is now a source of carbon, even though the last slide I showed you, which is from an older publication, showed a net sink. So the blue bar is showing the net release in petagrams of carbon, and in grams carbon per meter squared per day for that region. And then what they've done, which is clever, is they've said, okay, how much of that is the source from fires, which emit carbon monoxide as well as carbon dioxide. And so the red bar is where they've used carbon monoxide and emission ratios to say how much is deforestation release. And the difference between the net flux and the release flux has to be what the vegetation did. And so they're inferring net small sinks in vegetation in several parts of the Amazon, and a net release in the southeastern Amazon, where most of the deforestation and warming is taking place. So what are we doing? This is the triangle in the middle of all this, is a new platform for making these high precision observations of small changes in CO2 concentration and using winds to say what the net flux regionally is for the several hundred kilometers around the tower. So this is a platform that's 325 meters tall that will be used to augment the aircraft measurements. And it's a continuous platform as opposed to biweekly. So we hope to get more information about the causes of variations that are seen with the other techniques. The other way you can estimate the Amazon carbon sink, and the way you can understand what processes might be responsible for this forest uptake of carbon, is really relies on bottom-up, what we call bottom-up measurements. So people go out in the field, they measure the diameter of trees and how that expands over time. They also measure which trees got large enough to be included in the inventory and which trees died. And so you can make a change in biomass over time for a small plot of land that you study very carefully. And then if you take that and you multiply times, the area with forests like yours, the permanent plot studies of basically early in the 2000s, they were showing large net accumulation of biomass in these plots. But since in the last decade, increased mortality has reduced those estimates until in the eastern Amazon, they're almost zero or maybe losing carbon instead of growing over time. You can also look at the amount of carbon in soils, and you know, we also look at the age of carbon in soils and look at some of the growth rates of trees using our carbon 14 tool. But this is highly uncertain because it requires the extrapolation of measurements over made in a small fraction of area over a huge area. And what's happening now is that satellites, in particular ones that will allow us to measure biomass or tree height changes more over larger areas, are going to help a lot in reducing the uncertainties. Another thing that we're doing is saying, well, you know, some of these plot measurements might be a little bit biased, especially in the beginning, if they don't account for the disturbance and recovery and sort of succession dynamics natural to tropical forests. And one of the largest natural disturbances is by wind, when you have large convective storms that can flatten many, up to 100 hectares of trees, often in very remote areas. And so we have a group of researchers who are students here at the Max Planck Institute for Biogeochemistry who are doing really tough field work to look at in the past with satellite records to see where these have occurred and then how long it takes for the biomass to regrow. They're also studying species and what this does to influence the biodiversity of forests. So the main message here is that if you're in the Western Amazon near Iquitos in Peru, you would recover the biomass in about 20 years, whereas if you're in Central Amazon tropical forest near the Ato Tower, it's going to take a lot longer, maybe 40 years. And so we can start to say, okay, the balance of disturbance and recovery across the landscape, if we can map that, we can also understand how this influenced the large-scale carbon balance regionally. So those are the tools that we use to say what's happening now, but what we really want to do is predict the future. And for that, we have to understand some of the feedbacks between climate change, what the vegetation is going to do, and the amount of carbon dioxide in the atmosphere. And so here also we have to understand that there's a climatic effect when we say take forest and convert it to a pasture, as you see here. So the forest is a continuous green canopy. It's green throughout the year. It evaporates water throughout the year, whereas the pasture that replaces or the cropland, the grasses and crops don't have such deep roots. They don't transpire water in the dry season, so they heat up as a result. So it's warmer. You tend to have fire spread more readily. And of course, there's less carbon on the landscape. So even though you reflect a little bit more incoming solar radiation from this lighter surface, the evaporation is really what determines the fact that you're warming areas when you deforest. So replacement of the tropical forest means a warmer and drier climate. Warmer and drier climates tend to mean more fire, loss of biomass. That adds CO2 to the atmosphere. That increases atmospheric CO2 and warms climate. So you have kind of an additive effect that warming would tend to increase the amount of CO2 in the atmosphere or reduce the rates of uptake. The other feedback that we think about is that as we increase the amount of CO2 in the atmosphere, that can increase plant growth and storage of carbon on land, because if there's enough other nitrogen, phosphorus around, increasing CO2 will cause greater photosynthesis and in some experiments, greater growth. So that tends to offset the growth of CO2 in the atmosphere and be a negative feedback. So when we put these into our global models of land carbon balance, you can see that our predictions, our understanding is poor, and thus our predictions are all over the map. So this is from one of the CMIP model comparisons of coupled carbon climate models. Some of the differences are due to climate, but most are due to the feedbacks that are implemented and how they interact with climate. So this is the projected land flux for all these models. 0 would be the land is in net carbon balance, and that was thought to be the case up until, sort of the 1950s when we started to increase CO2 in the atmosphere. These models would say that much of the sort of 2 petagrams per year, that's what's observed sort of now as the land carbon flux, that's due to this CO2 fertilization process. And a lot of these models store carbon until mid-century, when the warming effect sort of kicks in and takes over, and we start to lose carbon from these systems. But you can see there's extremes. We can either be accumulating carbon at rates that are similar to what we're emitting as fossil fuels now. That's a very optimistic scenario. But there's also a very pessimistic scenario that we would be losing carbon that would almost double our fossil fuel emissions today. And I would argue we can't quite totally say which of these is more correct without more information. So one of the things our group has been doing is to look at how long this takes. So how long it takes a carbon atom once it's fixed to either be returned to the atmosphere through plant respiration relatively quickly, or to get built into say tree stems that last for 100 years that then have to decompose or burn to return the carbon to the atmosphere. And so I'm interested in those time lags. And a very short story is we use the bomb radiocarbon. So carbon-14 in the atmosphere is the black curve here. It approximately doubled in amount. So it's made naturally, and that's the basis of radiocarbon dating. But explosion of thermonuclear weapons about doubled the amount of C14 in the atmosphere, and we have this nice isotope pulse for the whole Earth system that declines over time as that excess C14 gets taken up by plants, dissolves in the oceans. And so when we make measurements, for example, of the amount of carbon dioxide or the carbon dioxide being respired from ecosystems, it's higher than what would be going in fixed by CO2, which is the black line, which is the atmosphere. And so what we can do is say how many years previously, on average, was the carbon being respired fixed. And I don't have time to go through all this, but if we put this together for an Amazon rainforest, we learned 2 surprises. One is that a lot more respiration, a lot more of the photosynthesized carbon goes directly into the atmosphere than we thought, which kind of reduces the carbon storage potential for these systems. And also that we have a kind of long age tail distribution for what remains in the system, largely because of what goes into wood. And if we put that in one of these very simplistic models and have the inputs increase with CO2, the time lag that we have is just how long it takes outputs to catch up to the increased inputs. And in the meantime, you're storing carbon. So we can calculate for a forest like the ones in the central Amazon, what's the rate at which they're storing carbon in vegetation and soils. And we can argue a lot about what the sensitivity factor is for CO2 in these systems. And in fact, there's an Amazon free air CO2 enrichment experiment that's starting hopefully in the next year or two to test this, because it's a big unknown for tropical ecosystems, whether they actually respond to increased CO2. But the outcome of this is really that the capacity to store carbon, even a relatively optimistically, would say that the CO2 fertilization is only partially responsible for the uptake that was observed in intact forest, and it can't explain the whole thing, although you'll read that in some of the papers. And the other thing we've done is to look at soil carbon sinks globally and show that most models are overestimating those that were used in the CMIP models. So I just want to take a last few minutes to talk about what we're going to do with the Balzan prize money. So, and here's where we want to start to look at the arc of deforestation region, which is really sort of ground zero for whether vegetation is going to change in the Amazon. So we're working in the state of Mato Grosso, which looks like this now from the air. So patches of remnant forest. There was more than 26% of this region was deforested. And as a result of the loss of evaporation in the dry season rainfall is down 24%. And dry season temperatures are up about 2.5 degrees Celsius, whereas the background warming is, of course, a lot less. So this is kind of ground zero for climate change. A lot of these forests are now close to an edge, and those edges simulate even hotter, drier conditions of the future. And so one of our goals is to look at this. We're also taking advantage of earlier experiments that disturbed these forests and degraded them with fire, and also experienced this wind throw damage, which was much greater in the places that had been burned and closer to the edges. So it seems like disturbance begets disturbance, and once you're in a cycle of degradation, that's really our question: what will be the future of these forests? And of course, the biomass that stores carbon in them. So here's our initial forest, the degradation, and the real question is, will these forests recover or go to a new stable state? And what are the consequences both for regional climate, biodiversity, and crop resilience in adjacent regions? And so this is what the edges of one of these highly disturbed plots looks like now. There's always been this debate about whether the Amazon of the future will become a savanna. This looks a lot like a savanna, but if you compare it to the nearby real savannas, the mix of species is completely different. So it's a novel ecosystem that we don't know where it becomes stable or whether it recovers. So I just want to leave you with two things to think about. We really are at a point where humanity knows what it's doing. With the upcoming COP 26 in Glasgow, we have a chance to agree to reduce emissions or to agree to live with the consequences. And those consequences will include a lot more warming if we keep going as we are, and that will do things to the vegetation around us and on which we depend, as well as to water resources. So we've been studying, that's our goal right now, is to study what the consequences will be. The other thing I want to do is, a lot of people say, oh, we can manage the land to take up carbon, but our experience is that it takes very short amount of time to lose carbon from these ecosystems, but it takes a long time to regrow a forest. It takes a day to burn it. So that we need to emphasize policies that don't just reward slow carbon storage in degraded areas, but maintain high carbon reserves where they exist. We also can make choices about what we do that drive these land use changes that are causing a lot of the increased deforestation now in the Amazon after years of reductions that were quite good. And finally, what gives me hope these days are the young people that we work with. These are some of the people that are working on the Balzan project for the future. They are the people who will have to live with the world we give them, and they need us to act, even if we're not quite certain what's going to happen. So with that, I'll stop, and thank you very much for your attention.